Okay. Welcome everybody to the seminar. I hope you can hear me well. I think most of you know me since I'm working in Dörrabere since November last year. For those who are not, so my name is JP, and I somehow a plant or forest ecologist with background in genetics and also remote sensing. And what I will show you today is a work that I did together with Jan, and which we presented also last week at the EGU 2020 General Assembly, which didn't took place in Vienna this time, but instead in my living room. And I added some more information in this presentation, but the core of the presentation is the same that I showed last week, actually. So as you can see, actually, from the introductory slide, there were many, many institutions involved. And we are also going to submit this work in the very next days as a manuscript draft to agricultural and forest meteorology. So why did we carry out all this work, actually? Is, as most of you probably know, is that the forest understory is still something which is poorly investigated. This is related to the fact that the understory has a obscure character and is very difficult to being measured in like destructively in a destructive manner. Okay. Especially when like mosses and lichens are involved. Another point is that there were some approaches to derive understory leaf area index from satellite data or remotely sensed data. But the problem is that this is going well in areas where the influence of the overstory is small. Okay. But we know actually that there are also productive forest sites with a very dense layer of understory, which you will probably never be able to assess with remotely sensed data. So there were some attempts in the recent past to determine leaf area index for the understory, but nobody really knows how they compare, and therefore we wanted to test this. Another motivation is, of course, that like as ecologists, we know that overstory and understory vegetation have different residence times for carbon. They can also have asynchronous phenology, which makes it in particular difficult to determine start and end of the growing season from remotely sensed data, because you never know if the signal that you get comes from the understory, which has probably emerged a little bit earlier than the overstory or not. And so, especially for carbon balance modeling, I gave you this formula here from a paper from 2007. So when you see how net primary productivity is currently determined in forest ecology, it's like that. So you can quite well assess the foliage, the wood fraction, and also the root fraction of the overstory. And then you have this term which is called MNPP, which resembles a little bit like the residual error term in a statistical model. And it's exactly treated in that way. So in this MNPP term, it's usually everything stored, which is difficult to measure, like flowers, seeds, fruits, and also the understory. So it's a little bit, I would say that the understory is stepmotherly treated in current carbon balance models. But we know from some ecosystems, for instance, like boreal ecosystems at high latitudes, that the understory can contribute a lot to the whole carbon budget. And we think that like finding a method which is able to capture leaf area index of the understory well could also assist like researchers and station managers of these forest ecosystem, ICOS, and greenhouse gas emission sites. Wait. So now what is this? Why is it not going forward now? So I have a small problem here because the slide is not moving forward. I don't know why. So something got stuck here. I don't know what happened. The slides are not moving forward any longer. Lea, do you have an advice for me?
I have no idea, but maybe you can try to switch off slideshow mode and then switch on again, or just to show in not the full screen mode.
Yeah.
Maybe it's then.
So at the moment, it's doing nothing any longer. Pity. You cannot even. Oh. So let me try to end slideshow.
We can see you now.
Yeah, but I don't know. Yeah, the slideshow. Ooh. So I just switched it off for a second and we'll start to try it again.
Yes, I think it's the best choice now.
Mm-hmm. Okay. So now I hope you can see the next slide now.
Yes.
Yeah. Okay. Sorry for this. So this is the scheme I wanted to show you. This is how we did this. Okay. So you see these colored points here on this map, and every point represents the footprint of one ICOS tower where we assembled our data set. And what you can see easily, I included some of the pictures of the understories here. So of course we have chosen these 29 ICOS sites in order to capture most variation, like geographically, in understory leaf area index that we can get. So you can see actually that the leaf area index among these ICOS towers differ a lot in abundance, in texture, and so on. So this was the reason why we did that. Okay, and then you can see here that so what we did, we organized two 50-meter long linear transects at each site, and we assembled reflectance measurements each 2 meter and digital ground pictures each 8 meters. Okay, and then we had actually 3 different methods that we compared, and I will briefly introduce them. So the first one is based on the fractional vegetation cover. there is it's basically the Beer-Lambert law of light absorption, and the formula is given here as -2 times the logarithm of 1 minus the fractional vegetation cover, which is based on this function here in the upper right corner. I think if Andres is in the audience, he will know this equation quite well. So just to explain briefly how we come to this equation. So usually it's the other way around. You determine actually the surface vegetation cover by leaf area index, okay? And then you have this parameter here, G0, which is the Ross-Nielsen geometry function. And mu0 is the cosine of the viewing angle. And when you assume that this G0 is 0.5, which would represent like a spherical distribution of leaf angles, and the cosine of 0, which is our viewing angle at nadir view, is 1, okay? And then you simply bring L, so this leaf area index, to the left side and W to the right side, and then you get this formula here, okay? And technically, how did we arrange to determine the fractional vegetation cover from the digital ground photography? So I showed you this here. On the left side is the original picture. And then what we did with some image analysis software is we masked out actually all photosynthetically active tissue. So in this example, you can nicely see that there's some beech forest with Anemone nemorosa vegetation. So you can even see the white flowers, and the right picture is the modified picture. So you see that everything which is white in the left panel on the left picture remains white on the right, and only the green tissue is masked out, okay? And then we use this analyze particles function, which can give you the fractional vegetation cover, like in percentage of the whole area, okay? And the second method, which we called LAI NDVI, is based on the NDVI vegetation index, as the name probably assumes. And for this, we employed the canopy radiative transfer model FLICE, which was developed by Hideki Kobayashi and colleagues. And in this canopy radiative transfer model, they modeled like a homogeneous vegetation structure which is dominated by shrubs and grasses, okay? And then they like parameterize this model with reflectance and transmittance that they got from empirical studies for grasses and for shrubs. And then they simulated near infrared and reflectances. And from these, they calculated NDVIs. And then via model inversion, you can, if you have your NDVI from a survey, like in our case, from our surface reflections measurements, you can take the leaf area index from the lookup table, okay? This is the second method. And the third method is also based on the vegetation index, the simple ratio. And this is a little bit more complex, but I will just briefly explain what the idea behind was. So this Deng and their colleagues, they developed this method because they wanted to retrieve understory leaf area index, like for global applications from remotely sensed data. And they argued actually that, well, when you have like canopy reflectance or radiative transfer models, then the accuracy of your leaf area index that you retrieve is highly dependent on the dimension of the lookup tables, okay? And they argued, well, when you have like huge data sets, then you would need also like huge lookup tables, and this will make computation, will drop your computation down actually. And therefore they developed a method which is based on only few iterations, okay? And the second improvement was actually that they argued, well, in these common leaf area index products that you get, okay, in these products, usually the product itself is forced to a common viewing geometry, okay? Like also in this NDVI method, you have like lookup tables only for some viewing angle and some zenith angle combinations. But they were able actually to develop a method where they could incorporate directly the data of the bidirectional reflectance distribution function. Okay, and they were not dependent any longer on like geometric normalization. This was the idea behind. And then we developed two tasks for our project. The first task was, well, we wanted to know how do these three methods correlate, and where are the limits where they agree and where are the limits where they disagree. This is important when you make like some recommendations to people that want to determine leaf area index in their sites, like in these ICOS sites or whatever. And so when they are not used to leaf area index as a biological quantity, we wanted to know whether it makes a difference if you use one or the other method at specific leaf area index ranges, for example. Okay, this is related to this third question here. And the second task is more, so we see this more like a small look into the future, was we wanted to see, well, we have this big geographical diversity panel of leaf area index. So can we relate the variation that we see also to differences in biogeography, for instance, like long-term climatic variables? Okay, so is leaf area index of the understory a function of long-term climatic variables? Because if so, and you find a very strong relationship, then you could also think about to approximate leaf area index of the understory by some other parameters that you get more easily, like, I don't know, like mean annual temperature or mean annual precipitation or whatever, okay? And the second question in this task B, what we wanted to answer is there a relationship between leaf area index of the understory and species richness, okay? You know, probably that, you know, there are many other remote sensing products that try to employ data from reflectance or whatever in order to make some statements about vegetation diversity, and we simply wanted to test this with our data set as well for the understory. Okay, so then I will directly come to some results. So what you see here in this upper panel is simply the pairwise correlation between the three methods and some model statistics. So what you see from these first three panels, A, B, and C, is that all of these methods are somehow related to each other, okay? Which is nice to know, because it simply shows that they are not producing simply random results. But what you see also is that you cannot really say something about the accuracy just by producing some correlation plots, okay? And therefore, we went one step further and we produced these Blend-Altman statistics. So for those of you who are not familiar with Blend-Altman statistics, Blend-Altman statistics are usually used in clinical studies. So when you would like to test a new diagnosis method in comparison to another one or to an older one, and you want to know how much the results will be biased by the new method in comparison to the old method, you calculate the mean bias and proportional bias, which are represented by this red dashed line and blue dashed lines here. So the red dashed line, these lower panels, they show the mean bias, the pairwise mean bias between each two methods. And then you have these blue dashed lines, which are the proportional biases. and they're nothing else than the 95% confidence interval of of the error between the two methods. Okay, and every time a point goes below or above these blue lines, you can then define, oh well, this is actually the range where the two methods statistically or significantly disagree. Okay, and then you can make also assumptions or statements about, well, one method should be used in one range and the other method should be used in another range. Okay, so what you can see from these plots D to F is very interesting. So what you see in plot D and F are 2 points which are falling outside these confidence intervals. And in each of both cases, the NDVI method is involved actually, okay? Which means that there's something going on which is NDVI method. And it means that the NDVI method gives considerably larger values at LAI ranges above 2 approximately. So for instance, at this plot F, you can see that here between 2 and 3, actually, the NDVI method is significantly upwards biased. Okay. Another thing which you cannot really derive from this picture here, from this figure, but from the next one, is that the simple ratio method systematically overestimates at very low LAI ranges. I will show you this from the next slide. Yeah, maybe one more comment. So what you see, what is obvious is that, of course, the NDVI method and the SR method, they are much more correlated to each other compared to the fractional cover. Okay, but I think this is it's not very surprising, because both vegetation indices show somehow the same reflectance data, and therefore I show you this plot as well. So of course the simple ratio and the NDVI in our data set, they are highly correlated anyhow, and therefore also the leaf area index product must be more closely. Okay, so it's not surprising. So, but what is interesting to see is when you show the derived leaf area index as a function of the main parameter of each of the models. Okay, so then what you see actually is, for the NDVI method, you see these 2 points here at very high LAI ranges, which is what I mentioned already before, is that at high ranges, okay, because of this strong exponential character of this NDVI model, is that at high ranges you get really unrealistically high values for the leaf area index, the understory. Okay, and on the other hand, when you go to the simple ratio method, you see actually that in this square here, so actually until or let's see, below 0.5 leaf area index units, you see that there's no data at all. Okay, and this means that the simple ratio method is not able to capture leaf area index at very low ranges. I will show you this on an example in the next slide, what it means. So here I included 4 pictures from one of our sites in France, and in Hesse, which is a dense beech forest with only very sparse understory vegetation. You see, of course, we have more pictures. I only included 4 because they are really very representative of the rest. So what you see is we have actually presence of litter and only very sparse blackberry vegetation. Okay, and then here on the right, I showed you actually how the 3 methods have determined leaf area index. So I think even for somebody who has no idea of what understory leaf area index is, I think it's quite clear that, like 0.5 is an I would say severe overestimation of the leaf area index at this site. Okay, so you see even this even the NDVI method with 0.06, I think, is quite optimistic. And I think the fractional cover captures this most well in this case, I would say. Okay, and this is the problem with the simple ratio method, that when you have actually presence of bare soil or litter, this will tune your near infrared signal up, and then the simple ratio increases. I wouldn't say exponentially, but more strongly than NDVI and fractional cover. Okay. So one more comment on this simple ratio method. As you have probably seen from the slides before, is that since this was developed for global applications, it is cover type dependent. Okay, so the coefficients that you take from these small lookup tables from the SR method, so they are tuned for or parameterized for different cover types. Okay, and you can actually distinguish for different cover types for understory and overstory. Okay, and so we wanted to explore also what difference does it make actually if we assume that our sites belong to one or to another class. Okay, because you cannot really fit them all into one, but you can also not assume, on the other hand, you cannot assume a different cover type for each single site that we analyzed. Okay, and therefore we simply assumed 3 different cover types for each site and then explored the variation that we got actually. Okay, so what you see here, so we did this actually for 3 cover types that most likely resembled what we analyzed, which is like closed shrubland, open shrubland, and forest savanna. And what you see at low or intermediate LAI ranges, you see that they are, I would say, reasonably close together. Okay, but when you go to higher LAI ranges, you see that, of course, the open shrubland and closed shrubland gives you higher values, and this forest savanna has a little bit lower values. On average, when you calculate the standard deviation over all sites among these 3 cover types, we found actually that it's making up for 0.05 leaf area index units. Okay, and therefore we think, well, it doesn't really matter if you take one or the other one. If you take one or the other cover type, it gives you, I would say, in all 3 cases, reasonable estimates. Okay, but nevertheless, you should be cautious if you use this method and really think about which cover type to use. So then I come to task number B, which was the relation of the leaf area index with the biogeography of the sites and also with vegetation diversity. So interestingly, so we employed a climate data set from Chakraborty et al., which provided 83 long-term climatic variables with 1 square kilometer spatial resolution over Europe, and we took the values actually of the 1 square kilometer grid where our site has fallen into, and then we made some kind of a reduced the complexity of all these variables by simply producing principal components of these 83 long-term climatic variables. Okay, and then what you get is like the first 2 principal components. So PC1 was more related to variables that related to temperature, and PC2 was more related to variables that relate to precipitation. But in both cases, the relationship between leaf area index and climate was very weak, actually. Okay, and therefore we concluded, leaf area index of the understory is largely decoupled from differences in bioclimatic gradients. Okay, so it's probably more related to some adaptation to shade regimes or whatever, but it's certainly not a function of site climate. Okay, so we know that for the overstory this is different. We know that height growth, for instance, of the overstory is strongly determined by differences in site climate, for instance, cold hardiness and so on, or minimum temperature of the coldest months. This is for trees is quite important, but for the overstory, for the understory, it's obviously not, which is also an interesting finding. But, and this is the second point, so we determined species richness at our sites, and we found that all three methods show a significant relationship with species richness. So which means that the more species you have at your site, the higher is your leaf area index. And it depends actually on the need of your desired analysis, how you would employ this relationship. Of course, this is done only for 29 data points, so we have a little bit of scatter here. There's absolutely no question. But we think for the future, this is quite an interesting finding, because you could actually explore this beta diversity more deeply in the future by analyzing also leaf area index. Okay, and yeah, so we see this more like a glimpse into the future. Okay. Okay, then maybe let me summarize the results from our work. So, of course, what we found is that all three methods are significantly correlated. But actually, there's one take-home message, and this is like this leaf area index retrieval based on NDVI is most likely unsuitable when you have very productive sites where your leaf area index is greater than 2. And on the other hand, the simple ratio method is very insensitive to low values of leaf area index, and especially sensitive to the presence of bare soil and litter. Okay. Interestingly, the most simple method, based on the fractional vegetation cover, seems to be a very good compromise. I mean, it's easy to understand, and it's capturing like both ends of the scale quite well. Okay, so you retrieve the low values, you retrieve the high values in a quite reasonable manner. But I have to say that you shouldn't forget that for the fractional vegetation cover method, you need to determine the fractional vegetation cover from digital pictures or digital photos. And this is actually not an easy task. Okay, so for the other ones, like measuring reflectances, is basically it's more or less a task of the device that you use, and then you get your data in an Excel table or whatever. But my feeling was actually that determining fractional vegetation cover, like with image analysis software, is easy as long as you have a good contrast between the soil and the vegetation. But in some cases, especially when mosses are involved, this becomes really, really challenging, and you cannot really batch process the pictures. So for some sites, you can do this, as I said, when you have a good contrast. But when you haven't, you really need to invest time in carefully fine-tuning the like masking process or outmasking process of the pixels. Okay. So this is the only drawback for the fractional vegetation cover method. And the last point is that, and as an interesting finding, we found actually that site climate has more or less nothing to do with abundance of understory vegetation or the leaf area index. But, and this is an interesting finding, and also I think for the future quite valuable, that species richness and leaf area index are related to each other. Okay, so species richness is, you can easily determine this parameter because it doesn't say anything about abundance. But I think for the future, when we could invest more time in like also determining other vegetation diversity parameters and maybe also gathering more data at other sites. I think this can be quite a nice direction for future research. Okay, that's it actually from my side. Just want to mention that this research was, of course, financed by the Estonian Research Council by 2 projects, actually. Yeah. And that's it from my side. Thank you very much for your attention. I hope that you could hear me well, and I'm happy to answer your questions. And thank you.
Thank you very much. And everybody can either ask the question or type it into the public chat as Tiit is already typing. But meanwhile, could you explain a little bit more the difference between NDVI and simple ratio methods? What else was different besides the vegetation index in those 2 methods?
Yeah, of course, there were many differences actually. So of course, the radiative transfer model that is used is also different in this simple ratio method. And then, so they are based on 4-scale simulations. But I mean, you know, I'm an ecologist. I'm not a physician. But so, in my opinion, actually, the whole computation procedure is, of course, more difficult because it's not dependent on lookup tables. But rather, you know, like tries to retrieve the leaf area index directly from the viewing angle combinations. Okay, and this, I think this is the major difference. It's simply, I would say, induces a little bit more demand for computation. That's it basically. Because you could see actually from the plot how strongly they are related, but you know, like I think only the shape of the curve for the model inversion is different, which leads to these substantially higher values for the NDVI method. Oh, sorry, there's one question I have to answer. Did you measure? Oh yeah, yeah. This is an interesting question. No, we did not measure overstory LAI at the sites. But what we are doing at the moment, I see Jan is also typing, so probably he's also giving a comment on that. But we are at the moment comparing also like remotely sensed products for these sites actually with our sites. Okay, this is not the overstory, of course, because this is everything what you can get. But I totally agree that overstory and understory. So I strongly assume that the stronger the overstory, the weaker will be the index of the understory. But this is a hypothesis that needs to be tested.
I take a. Do you hear me? That's Stefano.
I can hear you. Yeah.
Okay, perfect. So I'm the guy who is running the big tower. Maybe you have heard about that already.
Yeah.
Do you have any plans to make these kind of measurements also in Estonia? Because you pointed out also that there is a lot of problems when you have, let's say, a lot of understory plus mosses, because this is a very typical situation if we have here.
Yeah, that's a good question. So this is something. So since Jan is the project leader, maybe he should give a comment on that. This is true. So for mosses, actually, it's becoming more difficult. But I don't know. Maybe we can, you know, now we have like established this pipeline. So if we, and you know, the tower in Estonia is close by. So probably it's worth to simply test and because yeah, I think for you it would make sense to get an, I would say, reliable estimate of how much the understory would contribute to your carbon balance that you measure in the end.
Yeah, that's also, and also we have in our group in Life Science University, there is one lady. She has been dealing, I do not know if she's doing it on with so-called moss canopies. So she was, that's maybe also something what is an interesting impact, because there is this kind of leaf area index estimation on the small scale for mosses, which maybe in turn would be interested maybe for you if you see something there in this direction. So
yeah, absolutely, because of course for the mosses, the most challenging thing is actually to determine the fractional cover for the mosses, because usually you don't get really good contrast to the soil, and also like mosses are simply randomly organized. So if we could fine tune this like within the method a little bit more, this would for sure increase our estimate. But one thing I have to mention is that we don't have for any of the sites, we don't have any like ground truth. Okay, although I don't like this term to use, because everything is related or comes with an error. So what we simply can say at the moment is how much these methods deviate from each other, not from the truth. Okay, so it could be that the true LAI lies like much lower, much higher. I don't know. But at least I think what we know now is actually which method we should apply in which situation, and this is, I think, quite a valuable information.
Yeah, but yeah, Jan has already written, so I think we will have to make some visit to Tower one time.
Oh yeah, okay, fine.
Okay, let's have other people also.
Directly to a national application. So.
Okay.
Anything more?